This video is going to introduce Chapter 6, Thermochemistry. And just a reminder to make sure that you read the textbook for a little more of an explanation opposed to this introduction. So thermodynamics is the study of energy and how it's transformed. Thermochemistry is studying the relationship between a chemical reaction and the energy transfers, the energy changes that go along with it, and typically in the form of heat. So there's 4 laws of thermodynamics, 0th law through the 3rd law. The 0th law is really saying that temperature, the difference in temperature is a driving force for heat. So heat flows from hot to cold objects, and it will continue to do so until you reach a thermodynamic equilibrium where the temperatures are constant. The first law is that energy is conserved. It can't be created or destroyed. The second law is that in an isolated system, natural processes are spontaneous, meaning they occur naturally without outside intervention, anytime they lead to an increase in disorder, which is also called entropy. And we'll look at that more when we get to chapter 17. And the third law is that the entropy of a perfect crystal is 0 when the temperature of the crystal is equal to absolute 0. Essentially, absolute 0 is when all movement and all randomness stop and you have perfect order. Okay, so energy is the capacity to do work or produce heat. In physics, we think of it as 2 main types of energy: kinetic energy, energy of motion, or potential energy, energy due to position or how something is composed. In chemistry, we're really going to be concerning ourselves with the heat energy that's gained or lost during a chemical reaction. So a lot of times you'll see this delta sign, which is the Greek symbol, and for us it means the change in energy, how energies change from start to finish or from reactants to products throughout a reaction. Okay, and the SI unit for energy is the joule. Sometimes you might see problems with calories, which is also a unit of energy, but it's not really the SI unit. When we're talking about energy, you always kind of want to define what is the system, what are the molecules we want to study, and these are the molecules that are participating in the chemical reaction. And then everything else we consider to be surroundings. Anything else in the container that's not reacting, the container itself, everything beyond the container. So the system is what we're studying, the surroundings is everything else. Okay, most systems that we are going to look at are going to be closed systems, meaning that energy can exchange, heat can exchange, but not mass. You're not losing your products over time. Okay, so again, the first law of thermodynamics is conservation. Energy cannot be created or destroyed. So essentially, the energy of the system plus the surroundings is always constant. So any energy that's transferred from a system must be transferred to the surroundings. So what the system loses, the surroundings gain, and vice versa. Okay. Internal energy, which we give the symbol E, is the total energy of the system, which includes all kinetic and potential energies. It's really difficult or impossible to measure absolute internal energy, so we really are just going to look at the change in energy that occurs. So the final energy minus the initial energy would be your change in energy. Okay? Or when we're talking about a reaction, the products minus the reactants. Okay. If the change in energy is positive, meaning your final energy is greater than your initial energy, that means the system must have absorbed energy from the surroundings. If your system's absorbing energy, we say that it is an endergonic change. So this is similar to endothermic and exothermic, but we're talking about energy as a whole, not just in the form of heat. So anytime a system absorbs energy, it's endergonic. The opposite, if your delta E is negative, the system has released energy to the surroundings, and this is called exergonic. Okay, this would be similar to exothermic if it were just heat, but since we're talking about energy as a whole, we call it exergonic. There are 2 ways to transfer energy in and out of a system. One way is work. Work is applying a force to an object and causing it to move a distance. So force times distance is equal to the work. And another way is heat, and heat is thermal energy that's transferred from hotter to colder objects due to a temperature change, and this would keep happening until the temperatures become constant and you reach a thermodynamic equilibrium. Energy is therefore the capacity to do work or transfer heat. Okay, so in chemistry, we're really going to be concerning ourselves with the transfer of heat or the change of thermal energy in the system. Okay, just a sidebar, remember that temperature is a measure of average kinetic energy. All the particles or molecules in a sample are in motion. The more motion, the higher the average kinetic energy. As the temperature approaches zero, the average kinetic energy of the system will approach zero. Temperature is not a form of energy itself. It's just a measure of the average kinetic energy. The process of kinetic energy transfer at the particulate scale is called heat transfer. Okay. We can calculate the change in internal energy by this equation here. Okay, we said the energy could be transferred by work or heat, so the change in energy would be Q, the heat, plus W, the work that might have been lost or gained. Anytime we are depositing work or heat into the system, we're going to give them positive values, and it would cause a positive delta E. Anytime we are withdrawing heat or work from the system, that's going to decrease the internal energy and cause a negative delta E. So just again, sign conventions. If you are gaining heat, Q would be positive. If you are losing heat, Q would be negative. Okay. If work is done on the system, work is positive. If work is done by the system, it would be negative. So if you think of yourself working out, you being the system, you are losing calories because you are doing work. So anytime the system itself does work, it's negative. You're losing energy. And again, anytime delta E is positive, there's a gain in total energy. Delta E being negative, there's a net loss of energy. So take a moment, try these examples just using these sign conventions to calculate delta E, and check your work when you're done. So delta E is just Q plus W. It's telling me that W, 25 joules of work, is being done by the system, so that would be negative, and it's absorbing 10 joules of heat, so my heat would be a positive value. So I'm doing negative 25 plus 10 from my 10 joules from my heat, and I get negative 15. Okay, I'm just doing Q plus W, but putting in my signs based on this problem statement. For the second one, delta E, Q plus W again, but this time it's releasing 10 joules of heat, so that's a negative Q, and it's getting 25 joules of work done on it. That's a positive 25, that's positive work because work is being done on the system, so that gives me a positive 15 joule change here. Okay. Just as another side note about work, though we're not really going to be examining it too much in this chapter, there is different types of work that can be done on or by systems and involving chemical reactions. One of them is electrical work. Reactions can drive a current, especially if we're looking at redox reactions where you have a flow of electrons. A flow of electrons is electricity, so it can drive a current through a wire. Another type of work it can do is if you are producing a gas as one of your products, that gas would expand and it would press on the container, and so it would cause, that is a force essentially here. So you have expansion work. Volume expands during the course of a reaction when a gas is formed. And showing how to do that would be actually the change in volume times the pressure. The pressure it's expanding against times the change in volume, and I put that negative in there because the system, your product, the gas itself is doing the work, so that would create negative work. So that's why I put that sign in there. System's losing energy. Okay. If you're wondering, well, how do units of liters for volume and atmospheres for pressure turn into a unit of work? You can actually say that 1 liter atmosphere is equal to 101.3 joules. That's how it turns into, it actually is a unit of work, or can be converted to joules. It's a unit of energy. Okay, so you might want to take a moment and try these two simple problems just using that equation and check your work. So for A, you can do your work as negative P times the change in volume. Your pressure is expanding against is 2. Your volume change is 3, or 4 minus 1. And you get negative 6 liter atmospheres, and you get the same thing for B, so they would perform the same amount of work. And I put the negative sign in because the system is doing work. You could convert these to joules, but again, it would be the same number. So let's just talk about now narrowing our focus down to heat. If we're just talking about heat alone, an endothermic process is one that absorbs heat, so your Q would be positive. The temperature of the surroundings would go down. So if your system is absorbing heat, your surroundings would go down. So if this were happening in a beaker or a test tube or whatever, that beaker or test tube would get colder to your touch because you would be feeling the surroundings. Your hand itself would be part of the surroundings. So this would be a reaction could drive an instant ice pack. Okay, an exothermic process is one that releases heat into the surroundings. Your Q is negative. So since heat's being released into the surroundings, the temperature of the surroundings would go up and get hotter. So it would feel hotter to your touch, something that could create an instant hot pack. Delta H is called the enthalpy change of the reaction, and it has a definition as being the internal energy change plus the work of expansion from gases. But if you carry out a reaction at constant pressure, okay, if you follow in your textbook, there's a whole derivation, but essentially what it comes down to is that as long as you're at constant pressure, you're not changing the pressure, your enthalpy change just becomes equal to Q. The takeaway is at constant pressure, the change in enthalpy is just the heat gained or lost in the reaction. And open containers are always under constant pressure, so if we're carrying something out in an open container, you know that your delta H is just going to be the heat lost or gained in the reaction. And this is going to be an important takeaway when we're doing a lab calorimetry experiment, which we will do in this chapter. So if you see delta H, that's really just going to be your heat lost or gained for that reaction. Okay, your delta H is going to have units of kilojoules per mole. So it's the heat lost per mole. Okay, so delta H enthalpy is just the heat transfer between the systems and surroundings carried at constant pressure. Delta H is positive for endothermic reactions, just like how we say Q is positive for endothermic. And delta H is negative for exothermic reactions. Okay, and you can also just justify the sign of positive or negative if you're given a word problem. If you see something about the cooling of the surroundings, the temperature of the surroundings go down, you say, oh, heat must have been released into the surroundings. That must be delta, the delta H must be negative. So you can also base the sign off of observations, which we'll do something like that in the lab too.